So we started a research on natural hydrogen last year, and we had a presentation in the technical conference. And I had a kind of slide showing the increase in public's interest in natural hydrogen. And that started really at the beginning of last year, 2023, after the publication of an article called Hidden Hydrogen. And I have another slide which shows kind of change in public's interest in natural hydrogen. It shows that our honeymoon period with natural hydrogen is over, but we are in kind of now a stable relationship with natural hydrogen. But the number of papers related to natural hydrogen published per year is increasing, and we can expect more papers coming out because of the new project started in the last few years. So it's really kind of becoming a challenge to keep up with, with the development in natural hydrogen research. And so what we are doing right now is to gather information and data related to natural hydrogen to understand how natural hydrogen systems work, and so that we can really evaluate its potential and compare the results size of different prospects reported in different, by different companies. So I talked about the trend in public's interest in natural hydrogen, and this is where we are. So this data is as of about 2 weeks ago. And as I said, the number of papers related to natural hydrogen published per year is increasing, and we expect more papers coming out because of the new project started in the last few years. But let's start with the definition or defining what we are going to talk about. So natural hydrogen is hydrogen naturally occurring in various environments in different forms, and they are generated through either biotic or abiotic processes without human intervention. So then there are more and more reports of highly concentrated natural hydrogen, and the distribution or the occurrence of natural hydrogen, such natural hydrogen is ubiquitous, and it's widely spread, and I believe it's one of the potential advantages of natural hydrogen. Now, this diagram is a little complicated, but what it shows is how to get manufactured hydrogen from primary energy sources and feedstocks, using production technologies and mitigation technologies. And what I want to point out is that in this diagram, at each step in the process, carbon footprint, water footprint, mineral requirement, land requirement, and energy loss increase. And the major difference between manufactured hydrogen and geological hydrogen is that natural hydrogen is primary energy source. You don't need to convert natural hydrogen into hydrogen. You can use it as is. Well, you still need to probably separate from other associated gases, but because it's a primary energy source, you can skip all these steps. So there's a chance that the production of natural hydrogen has smaller environmental footprint, and also we can use it without energy loss. Okay, so because of these, we see many papers or articles on natural hydrogen, and people are excited about, about natural hydrogen because it might be a new, clean energy source with burst potential. And such articles start with the story of discovery of natural hydrogen in Mali because of its exceptionally high hydrogen concentration, but also because it is the only pilot study which did the production of natural hydrogen, electricity generation using natural hydrogen, and they provided electricity to local community. So it's a nice, success story with an explosion with cigarette at the beginning, and there are other interesting facts about this field, and one of them is that there's an indication that the hydrogen is generated dynamically now based on the stable reservoir pressure after several years of production, and also the young age of hydrogen in reservoir. So you've probably seen some articles or people claiming that natural hydrogen is a new renewable energy source. I am not sure if it's really renewable, but I leave it to you to decide. And then, okay, so natural hydrogen seems to be exciting, a new energy source with burst potential. But where was it hiding? Why you are not studying natural hydrogen, right? And you've probably seen such comments before or heard people saying, but even if we limit ourselves to papers or reports written in English, there are reports with natural high concentration of hydrogen in like 30s or 40s. And there's also this article which listed already highly concentrated hydrogen occurrence. And this is my favorite, geothermal hydrogen in 80s, 90s, and early 2000. We had papers basically telling us to wake up and start looking for natural hydrogen. And the original paper on Murray field was published 6 years ago. So I agree with such statements that there was a prejudice that hydrogen cannot be trapped, and we simply ignored natural hydrogen. Much like ultra-deep water systems, we were not looking for petroleum systems on transitional crust and oceanic crust, and now all the companies are looking for such field. So, and it seems that the Murray field is not a one-off. There are reports of prospects with size similar to that of Murray field. These are here. And there are also studies now showing that hydrogen can be trapped and stored in subsurface. And the example of seals would be like a dolerite seals in Mali, or shale or clay stones in Kansas, or the thick evaporite layers in the Amadeus Basin in Australia. And all of us know that there are large sort of structures in both in Texas and Utah, which can serve as a good seed for hydrogen storage. So now you might be wondering the size of these prospects. And if you compare them to oil and gas, they are not massive, they are not gigantic. However, this comparison is also not valid because probably you cannot see, but we do not have a standardized way to do an evaluation of reserve size for natural hydrogen system. So we are not comparing apple to apple. These are all different estimates. And to have such standardized way to evaluate natural hydrogen prospects or fields, we need to understand how natural hydrogen systems work. And that is what we are doing right now. So we are gathering information and data. We are collecting the information about the analogs that we could use. We are also collecting information about processes of natural hydrogen systems. And the goal of this project is to really understand how natural hydrogen systems work, identify the knowledge gaps, and come up with new ideas for research project. So I think we all agree that the basic concepts of petroleum system can be applied to natural hydrogen system. There are source, there are reservoirs, there are cap rocks, and there are processes like generation, expulsion, migration, accumulation. There are also consumption too. But if you compare them closely, then there are many unknown, there are many known differences because hydrogen is more diffusive, it's more reactive, they behave differently, for example, in reservoir. And also, we expect more unknown differences that we are not aware of, and also knowledge gaps that we would like to identify as this project progress. So, as part of this project, we are also developing a new method for natural hydrogen exploration. And with this slide, I will.
Awesome, thank you. For those of you that didn't see me wipe out, do not try and climb up here. Please use the stairs, public announcement. Okay, hi, I'm Dr. Bryony Richards. I'm an advanced imaging expert and economic geologist from the University of Utah at EGI. Eiichi and I have been working on natural hydrogen exploration for about a year now. And we found some really exciting ways to not only look for natural hydrogen and assess whether depressions and fairy circles, whichever one you want to call them, I prefer fairy circles, whether they're productive or not, whether they have a life cycle, which we now know they do, and also to kind of try and quantify how much hydrogen is coming out of the seeps using mineral proxy-based hyperspectral imaging. So this shows a little bit of the workflow. Obviously, you need to get the imaging first. You can do that using satellites, which is very nice because it's free public data for the majority of the time. You can use airborne planes. Avaris, the NASA plane, is one of those examples. And you can also use drones, which we will be hopefully utilizing next year. After that, there's a fairly simple methodology. And this has been published before. I believe, what was the paper, Eiichi? Can you remember the paper that this comes out of? Or is this is your methodology? This is ours. We've seen some with the sort of reconnaissance characterization, but the idea of putting hyperspectral imaging into this is new. So you might be asking, what is hyperspectral imaging? It is imaging. I'm going to skip to this slide first. It was introduced in the 1990s. You might remember things like the Landsat and Aster satellites. We're now on Landsat 8. Aster, the satellite, is kind of defunct. It sort of went out of service in 2008 for some of its bandwidths. You can think of hyperspectral imaging as a continuous rainbow. So you have RGB, that's what we're used to on things like TVs and our cell phones. You can have multispectral imaging, and that goes up to 37 bands of wavelength light. Or in hyperspectral, you can have more than 37 bands, and this is based on the USGS. I often get asked, if it was introduced in the 90s, why are we using it so much now? And my answer to that is computing power. We've only just kind of reached this axis, where you have both the computing power and the data. Then the problem is you need the expertise to read the data. And so you kind of need to be a mineralogist on top of that. So it's a combination of mineralogy, imaging, and computing power. So it's a really difficult trifecta for people to learn. If we use it in terms of a landscape, you can imagine that the satellite is pushing a broom along. That's how we sort of measure the pixels. It's called a push broom sensor. With that, every single pixel, doesn't matter what's on the ground, whether it's a rock, a human, or a cow, it all reflects. And it gives us a very distinct reflection signal, and you can see that there. What we then do is pick out those parts of the spectra that are significant for minerals or snow studies or water studies or whatever you want to do. And if you have enough data, you can start to make incredibly detailed mineralogical maps. The map you see on this is actually Yellowstone. So that is the gram prismatic area. The diameter of the picture is about 1 mile. So this is, as far as I know, the most detailed geological map of gram prismatic. As I said, we use a variety of different methods, and the really good thing about this is that you need to cross-correlate. With hyperspectral imaging, you need to understand the satellites, you need to understand the spectral properties of the minerals, and you need to cross-correlate to check your work. You need to ground truth. Now, the best ground truthing is obviously going and getting rocks. But as you'll see, a lot of our fairy circles are not in places we can go get samples. So we use multiple methods to cross-check our spectral imaging, and geological maps, and things like MINDAT, where rock hounders have picked up rocks. That's also useful. As I said, we can't go to most of places where there are the large fairy circles. And the reason we've chosen these is that there's published data to go with these. So there are hydrogen measurements. And that was obviously very key with looking at hyperspectral and hydrogen. We need to make sure that we can cross-correlate and ground truth. So you've all heard of the Mali depressions. The very large depression from Mali that we'll talk about in a minute was discovered after someone lit a cigarette near the well. Apparently he's still alive, which is good to know. Probably doesn't like natural hydrogen anymore. We're also going to discuss some Russian circles and some Brazilian circles. The reason I include the Russian and the Brazilian so much in presentations is because they're vegetated. Most people who know hyperspectral imaging are terrified of vegetation because obviously it marks any signals that your rocks are trying to show you. This is the Mali circle. And this is personally my favorite because I think the analog is so good. I would prefix this with the data that was taken from Prinzhofer in 2008 is actually measurements from 2015. And our spectral data is from a decade later almost. So you're seeing a change in these fairy circles because they evolve. They kind of have a life cycle. And we see that, and we'll show you that in different slides. And they're very dynamic. If we're seeing a change over 10 years in the mineralogical surface changes, which is what we're looking at, then we know that below there is a very dynamic system. As you can see on this slide, our data from our spectral indices, and a spectral indice in this case is the visual representation of the mathematical equations of different spectra. So what we've done is not only use spectra to highlight certain minerals, we've then combined that to make sure that we look at different minerals that are affected by hydrogen. So we have multiple mineral signatures that we're looking at, in addition to a built-in vegetation reduction index. And that works very, very well. You'll see that the peaks correlate very nicely with the data. And the spectral index, where you get highs, you got highs in the Prinzhofer paper. So this was the first one we did, and we got really excited. But we needed to try another one. So I like to call this the Barbie figure. It's nice and pink, very pretty. The useful thing scientifically is it shows kind of an active fairy circle and a dying fairy circle. You can see that they look very different spectrally. And that's really important. So the blue one above the active fairy circle is unlikely to have that much hydrogen, or so we think. There are no measurements from the upper circle, so it's quite hard to tell. This spectral index was ridiculously complex, but what it does really well is show extinct fairy circles. And those kind of appear as ghostly white. And so this is very useful for us when we're kind of scanning an area to see the potential, seeing immediately where those trending extinct fairy circles are. We again put our spectral hydrogen alteration index onto this. There's a reason I'm not telling you what it is, and that's because we're about to publish on it. Again, this is a different paper. This is Larin 2015. And you can see again, does the laser pointer? No. You can see again that it picks up the trends of the actual hydrogen measurements within the spectral data. We then went one stage further with this and mineralogically mapped the lower fairy circle. There's also a very good geological sort of story here, and that's another part of the paper. So we can show you the colors, but we can't show you the minerals. If we apply a heat map to that black and white picture, it becomes much easier to see. When I put on the 3 stars, you can see that they're on structural boundaries of the fairy circle. No one really knows what those spectral boundaries represent. We think we know. So that again will be in a publication. It's likely to be subsurface as well. So we think it's both a mineralogical surface change, but also represents something subsurface. The next one is the Brazilian fairy circles. Unfortunately, no transects, but again, we have those very consistent patterns. This also very nicely shows a mega structure, and it shows how our index deals with vegetation, which is that it ignores it, which is what we want. You can see in Brazil, not only does the hyperspectral imaging pick up the fairy circles, but it picks up the larger basinal strike structure. And so this has already helped us to identify tens more of fairy circles in this basin, which is the São Francisco Basin. And I'm going to hand over to Eiichi.
Thank you. So just the final remark, I would say. So the research on natural hydrogen requires people from petroleum science, but also people who knows how to work with hot and hard rocks and how mineral and water reaction works. So I think in this room we have the right mixture of people, so I'm looking forward to have more discussion on natural hydrogen, and hopefully we can come up with nice research ideas. So thank you.
Absolutely fascinating talk. So thank you so much. Really appreciate this sort of exposition on natural hydrogen. We might have time for one very, very quick question. Christine.
Yeah, I hope this is an okay question, but the list that you showed and what you're telling us here, are any of these incidences of actually seeing the subsurface hydrogen on purpose, or are they all, you were looking at something else and wow, it's hydrogen?
So Mari's case is accidental. But there are like 30 or 40 exploration companies now doing active exploration. And yes, many of them found actually reviewing the old well reports. But they are kind of intentional. The activity was intentional. So yes, exploration is, I think, possible.